Hello everybody and welcome back to Advanced Functions. Today we'll be working on chapter 7.4, which revolves around techniques for solving logarithmic equations, which should be a lot of fun. Today is also one of the last content-driven things we have to learn about exponential and logarithmic equations. So again, I can't wait to teach you that, so let's get started. So chapter 7.4, as I said, revolves around the techniques for solving logarithmic equations. So first we're going to talk about how to solve simple logarithmic equations, and then we're going to talk about how we could apply factoring strategies to solve more complicated equations. Either way, both of these concepts are pretty simple once you get the gist of it, so do not worry, we'll take it slow and I'll go through it step by step. So first, let's talk about simple logarithmic equations. The most important thing we have to take away from every piece of work we've done thus far is that you can always express both sides of an equation using a logarithm of the same base. So you know when we were saying that you could take the log of both sides and that wouldn't change your outcome? Yeah, that's what we're talking about here. So if a is equals to b in some context, then we know that log of a has to equal to log of b, and vice versa. So if log of a is equals to log of b, then so does a equal to b. Using this property, we can actually solve any logarithm problem by expressing both sides as a logarithm of the same base, but we can also always use our tools we learned from last time of converting things from logarithms to exponential equations, and we already know how to solve exponential equations, so that shouldn't be a problem. So here I have two examples. Let's actually fix the formatting because it's really upsetting me. There you go. Sorry, I had to fix that. So our first example is right here. 4 is equals to 2 log of p plus 62. Immediately, what we could do is divide both sides by 2, because we know 4 is divisible by 2, and 2 is 2. That sounded great. So again, dividing 4 by 2, we get 2, and on this side, we would get log of p plus 62. Now, we can, for example, rewrite this as an exponential equation, right? So our base here is base of 10, because we know this is our common logarithm. And so the base is 10, our exponent has to be 2, and our answer is the things that were in the bracket. Therefore, we got 10 squared is equals to p plus 62. 10 squared is 100. Isolating for p would be the same as 100 minus this, and so that's what we wrote here. P is equals to 100 minus 62. That's simple arithmetics. And so we found out that p is equals to 38. Again, just like with any type of equation we've done before, we could graph this equation to see if it's true. So here I graphed or entered our equation. I had to write p as x because that's just something Desmos is picky about. But when we do this and we graph it, we actually see that our answer is a 38. Is that the same thing we got before? Yes, it is. So as you can see, both of our solutions are correct. Therefore, we did this whole thing correctly. Now we can do the same kind of process for question 2. This one might seem a little bit complicated, but it's really not. The only difference here is that we don't have an a value, but we have a c value, right? But either way, we're trying to isolate for x. So first we're going to take this plus 6, move it to the other side. So you could do 9 minus 6 is equals to this, but that's too much writing for me personally. So I just wrote 3 is equals to log of x plus 100 of base 5. Again, writing this as an exponential form, we have 5 as our base, 3 is our exponent, and whatever was in the brackets is our answer. 5 to the power of 3 is 125. We substitute that in, and so we get this here. Again, isolated for x is now just a mere moving plus 100 to this side. So 125 minus 100 is the same as 25. Therefore, we found that x is equals to 25. Again, you could enter this into decimals and make sure that it's true, but I feel like we don't need to do that because you could see the logic we followed rather easily. With that being said, if you understand these two concepts and how we've done them, we can easily move on to more complicated logarithmic equations. So sometimes you won't face pretty problems. There'll be exponents and radicals and fractions, and you'll be like, ew, I don't want to do that. But sadly, you'll have to. And so, for that reason, we must really pay close attention to our factoring. Why is that? Well, because factoring makes your life a whole lot easier. You never want to deal with large numbers. You never want to deal with ugly numbers either, and factoring allows us to remove them. So again, let's look at two examples I have written out here and see how they are solved. So our first equation is the following. Immediately, we see the radical. We don't want it there. So how can we express a square root? Well, we know a square root is the same as putting something to the power of 1 over 2, and that's what we have here. From this point, you're like, oh, a logarithm with a power, the power rule, move that boy to the other side. And so we took the 1/2, brought him to the other side, and now we have this equation here. If you really can't tell what's going on, I would recommend putting it on brackets, for example, here. So let's do this guy first. Again, it might get a little bit visually cluttered when you do this on a slides presentation like I am, which is why I always tell you to write these things down. It'll make your life a whole lot easier. Again, from here, we can actually divide both sides by 1 over 2. 1 over 2 divided by 1 over 2 is 1, so that's not here anymore. And then 1 divided by 1 over 2 is the same as 1 times 2, which is what we got on this side. Again, for this guy, let's just quickly rewrite it so it looks pretty and we can tell what's going on much easily, that the log is of the whole thing and not just of x squared. Now we sorted that out, we can go to either two of the strategies. So our first strategy might be to convert this to an exponent, like we had before, right? Easy, not complicated. So that's what I did here. Another way you could do this is actually find what log is equals to 2. So we have log of base 10 is equals to 2. We know that log of 100 is equals to 2. So you could put that on this side. Then since we have log on one side and log on another, we could actually get to this point. As you can see, it's a little bit more extra steps, but sometimes you'll have to do that because we won't have pretty numbers. But either way, let's move on. So 10 to the power of 2 is equals to x squared plus 48x. Expanding this and bringing it all to one side, we get x squared plus 48x minus 100, because that's what 10 to the power of 2 is equals to 0. From here, we don't want to work with this. We could either use the quadratic formula and solve for x, or we could remember our factoring rules. The factoring rules tell us that a times the c value will give us something, and then those two numbers that we use to get negative 100 would give us the same number in the middle if we were to add those two. So I actually found those two numbers really easily. Again, what multiplies to negative 100? First thought, 50 and negative 2, or negative 2 and 50. If it was negative 50 and 2, this would have negative 48. But it's positive 48, so it has to be positive 50 and negative 2. The standard form for these types of equations is x minus our values. And so x minus 50 is getting us negative 50, and then x minus 2 is getting us the 2. Pretty simple. So from here, we figured out that x could equal to negative 50 or x is equals to 2. Again, what we can do now is check whether or not those values fit into our function. How do we do that? Try them out. Plug in -50 into our first equation. See if that makes any sense. They should be a positive number minus a negative number, or minus a number that is less than 50 squared. So this radical makes sense, therefore that is a solution. This number here is two positives added to one another, still makes sense, therefore we have a solution. So both of these are valid answers. Now, if you understand how we did that, we can move on to question 2. So question 2 might seem a little bit complicated, but off the bat, we see a log of base 10 plus a log of base 10. What rule is that? That's the product law, right? We learned it last class, so let's apply it. We know that the product law just multiplies the two arguments within the brackets, and that's what we wrote here. Again, this one is even easier. We know that something, like if we write this in exponential form, we would have base 10 to the power of 1 is equals to what's within the brackets. That's what we get here. Remember, anything to the power of 1 is itself, so I didn't bother writing the 1. From here, I opened the brackets and moved the 10 to the other side. So we get x squared plus x minus 2 minus 10 is equals to 0. Collecting like terms, which is the -2 and the -10, we get x squared plus x minus 12 is equals to 0. Again, these are super simple numbers. We're thinking, hey, what multiplies to -12 and adds to 1? Well, that can only be 4 and -3. So that's what we get here. X plus 4 and x minus 3. Again, from these we solve for when x is equals to 0. So that would be when x is equals to -4 or x is equals to 3. This is very important for you to understand. X cannot equal to -4 for one reason and one reason only. If we were to substitute -4 into our original equation, we'd have log of -2 plus log of -5. Can we have the log of a negative number? Perhaps, but we have to pay attention to the asymptotes. The asymptotes here are -2 and 1. -4 is beyond the asymptote. We cannot get to that point, so it is not defined. Same thing goes for log of x minus 1. This asymptote is at 1, so there's nowhere we're getting an x value at -4. So that root is extraneous and we cannot provide it as a solution. Therefore, the only real answer we have is x is equals to 3. Again, we could verify this by graphing it. And would you look at that? We only have one answer, and that one answer is that x is equals to 3. Well, how did we get the other root then? You might be wondering. Well, let's graph this function. Log of x plus 2 times x minus 1. Let's put these into brackets. Remember, this is very important. There you go. And now this is equals to 1. Notice how now we have two roots, right? Let's get rid of the black line. We have two answers. And that is because when you get two negative numbers times each other, they make a positive. And so we can actually find the 1. But in the respective ranges, or the respective ranges of these two functions, that does not exist. So log of x plus 2, see, we can't have a -4. They'll never touch -4. So that's impossible. And then log of x minus 1, it's even farther away. It cannot get to -4. It'll never get there because the max it could go to is really close to 1, and this one will go really close to -2. So that is the most important thing you have to remember for this chapter. you can always state your restrictions at the start so you don't forget it. So for example, if you want to be extremely smart about it, you'd be like, oh yeah, you know what? When is this thing negative? Is it ever negative? It's never negative. So we shouldn't have any restrictions besides, getting less than 0. However, over here, we immediately have to say that x has to be greater or equal to -2, x has to be greater than -2, and x has to be greater than 1. Using those two defined ranges, we know that it has to be x is greater than 1. Because even if this is, for example, 0 minus 1, again, doesn't make sense in this context. So those two combined ranges have to form into 1. So if our answer fit into this part only, it wouldn't count because this still wouldn't make sense. So that's what you have to pay attention to. If you understand that, then you're gonna go and do amazingly in this chapter because we're essentially done. The homework for today are these 6 questions. They're not difficult. I've used all of these examples from the textbook, and as you can see, they do not take a long time. Some of these questions are word problems, but again, that is just to get you prepared for application questions on your tests or quizzes. If you have any questions, again, just feel free to leave a comment down below. I'll answer it as soon as I see it. Again, thank you so much for sticking around and listening to these lessons. I'm hoping you are doing well now that school has started and these have been helping you out. Either way, I can't wait to see you next time. Bye bye!